Greetings to you. We were looking at the Carl Fischer reaction in my last class. I had explained to you that Carl Fischer titration is carried out using iodine sulfur dioxide and pyridine, where the an inner complex is formed in presence of water, and that can be titrated to determine the concentration of water, because water reacts stoichiometrically in the whole reaction of the pyridinium salt formation. So, we looked at the apparatus also. The apparatus was very simple, using a very simple battery, microammeter, resistor and radio potentiometer. So, 80 millivolts across the electrodes should not be a problem, and it can be used until the battery is exhausted. Then you have to replace the battery and again start off. So, I had suggested that the reagent may be applied to the samples with the following requirements. They should not be reacting with the reagents or hydrogen iodide to yield water. This is one of the conditions now. So, the sample what you want to analyze should not be reacting with any of the reagents or hydrogen iodide HI to yield water. That is that will defeat the purpose of water analysis using Carl Fischer reagent. And the sample should be miscible with the reagent and preferably does not cause precipitation of the pyridine complex formed during the titration. This is also fairly simple to understand. They should be miscible with the reagent, do not cause precipitation. So, otherwise sample will be lost, pyridine will be lost, and they should also be able to conduct electric current. This is also one of the preconditions in case you are not able to do the titration. So, they must conduct the electric current. So, the reagent may be used for determining the water present in hydrated salts. Potassium tartrate is one of them, which we had used as a standard. I had mentioned earlier now, disodium tartrate dihydrate, and which is absorbed on the surface of the solids. We can determine that also. Some substances are there which will absorb water from the atmosphere. So, you quite often that is not desirable. So, quite often we would like to determine how much of water is absorbed and desorb it and then use it in our day to day life. Carl Fischer titration is one of the best methods, because it can determine ppm level of water, not in percentage or in grams or milligrams, it is in ppm. So, a sample of the powder containing 90 to 100 milligram of water can be dissolved and or suspended in methanol, and the mixture can be titrated very easily with Carl Fischer reagent to the usual electrometric endpoint. So, an endpoint is stable for about 15 seconds, should be more than enough to indicate that the reaction is complete. So, there is a certain waiting time of 15 minutes before you close the titration. And regarding the application of Carl Fischer titration, I can say that it has been successfully applied to the salts of barium, cadmium, cobalt, lead, magnesium, nickel, sodium, zinc, uranyl acetate, calcium lactate, calcium malonate, propionates, sodium citrate, naphthionates, succinates, formaldehyde, ammonium, list is endless. Phosphates, potassium, chromium, strontium, cadmium and tin chlorides, and then nitrates of chromium, cobalt and mercury. We can add add to the list aluminum, cobalt, iron, magnesium, manganese, nickel, zinc, as most of the sulfates. In short, what I want to tell you is, suppose a laboratory supplying company is there, they have to give a certificate for the contents, assay, water content, purity, impurities, etc., depending upon the whether the reagent is technical grade, NLR grade or laboratory grade or something like that. So, a chemical supplies laboratory will be supplying many of these salts what I had mentioned earlier for the consumers. So, normally any chemical analysis must accompany a chemical, that is the rule. Otherwise, we will not know what chemical we are handling if it does not have a label, and the label should also contain what are the impurities and what are the actual contents. So, if it contains water of hydration, it has to be mentioned. So, regularly lot of people use Karl Fischer titration in their factory. So, activated alumina is one of the standard that is used because it contains exactly 7.02 milligram per liter. Milligram per liter is ppm. Then I can use silica gel. I can use that contains 5.48 milligram per liter. Calcium chloride, that is about 11.28 milligram per liter, and calcium sulphate also can be used as standards. So, what are the interferences? The interferences are like this, that oxidizing agents such as chromates, dichromates, cupric and ferric salts, peroxides, etc. interfere. Why do they interfere? Because many of these are oxidizing agents. They oxidize iodide to iodine in presence of metals. Here first reaction I have written that MnO2 plus 4 molecules of pyridine plus 2I minus goes to Mn2 plus 4 molecules of pyridine plus iodine plus 2 water. Here the problem is not the preparation of the sample, but also it should not be reacting with pyridine and iodide. So, similarly, reducing agents such as thiosulfates, tin, sulfides, etc. should not be there. Basic oxides also react with pyridinium, C5H5NH ions, and then they give you zinc metal and water plus pyridine. This is not the Karl Fischer titration, because here the zinc reacts not with iodide iodine or pyridinium ion. So, it is typically not there is no water molecule, it is being produced here, but not getting reacted. Similarly, weak oxy acids NaHCO3, C5H5NH plus, all these things are NaHCO3, it is stable around pH 4. So, many of the salts, what we analyze them here usually contain they should not be reacting with pyridine, they should react with iodine. So, NaHCO3 cannot be analyzed weak oxy acids because they react to produce water. So, the more and more you analyze, more and more water will be produced. more of this pyridine will be consumed, and there will be problem in finding out when the reaction will end. So, we also cannot handle salts like this H3BO3 borates, H2BO3, H3BO3, because they react with methanol, which is one of the component of the Karl Fischer reagent. So, that reaction is given like this H3BO3 so this is an ester, methyl ester containing borate plus 3 molecules of water as a reaction product. That is also not very convenient. So, if I have to do a titration of Karl Fischer reagent, what do? I just take a small sample. I will give you an example, then you will be able to appreciate what are the problems. So, the example is like this. In the look at the slide, 1 ml of Karl Fischer reagent is equivalent to 6.66 milligram of water. So, if I have to titrate, I have added Karl Fischer reagent of 2 ml. So, excess is determined by the titration, and when I did this for a given sample, I got 1.18 milliliter of water methanol as a titrant. Finish, that is the excess. Now, how much is consumed? That is 0.54 ml. So, titer value I got is 1.46, that is 2 ml minus 0.54, that will be 1.46. So, water content I can calculate 1.46 multiplied by 0.66, and this 100 comes from percentage. To calculate the percentage, this 10 ml is the volume of the sample and 1000 is the per liter. So, that is to convert milligram into grams. So, if you do everything according to this calculation, you will end up with 0.098% of water weight by volume percentage, weight by volume. Okay. So, that is where we complete our discussion on this Karl Fischer reagent, and then we move on to the next module, that is ion selective electrodes. So, there is not much to tell about the ion selective electrodes, because it is something like extension of a glass electrode, but we can do wonders with many of the ion selective electrodes, because that permits us to determine unknown concentrations of the metal ions and non-metals also, sometimes gases, etc., using ion selective electrodes, because as the name suggests, ion selective electrode is that electrode which gives a response selectively to particular ions. So, if I want to determine sodium, I just need a sodium electrode, that is a glass electrode. So, potassium electrode, potassium, cadmium, cadmium electrode, like that. In the market, if you want to buy, there are many ion selective electrodes which you can plug into a pH meter, but not exactly a pH meter, it is something similar to pH meter, because for pH meter the range is somewhat fixed. For the reduction of ion selective electrodes, the reduction potential will be different. So, the meter would be different for compared to glass electrode. So, the indicator electrode of a cell is an electrode in which the potential depends upon the activity of a particular ionic species. This we already know, isn't it? The indicator electrode of any cell depends upon the activity coefficient or activity. What is activity? Activity coefficient F multiplied by the concentration, that is F into C. So, particular ionic species, that is the formula, and which is to be qualified. So, in potentiometry, a simple carefully cleaned metal rod or wire of the metal constitutes the electrode which is dipped into the solution, or it is just like glass electrode. What do I have here? In potentiometry, I take a metal rod and then dip it in a solution and then make the complete electrical arrangement with 2 electrodes and then batteries at the outside, external circuit, voltmeter and current meter and all those things. That is potentiometry. So, when hydrogen ions are involved, we have a hydrogen electrode that is specific for hydrogen, or a glass membrane is useful also. Here the potential developed between the surface of the glass membrane and a solution is a linear function of the pH of the solution, and hence it can be used to measure the pH of the sample. Since glass membranes contain alkali metals, that also can be used for alkali metal determination, just like we use it for hydrogen ion. So, why? Because the alkali metals also would be in equilibrium with the solution in the if it is alkaline. That is why we always say do not use a glass electrode in the alkaline range. There may be errors if you want to determine the pH. I had mentioned earlier that if you want to measure the pH of an alkaline solution, the error could be plus or minus 1 unit around pH 12. So, obviously at that range the electrode will be behaving as if it is in equilibrium in responding, or it is in equilibrium with the alkaline ions. Sodium, it may be sodium ion or potassium ion or ammonium ion, but glass electrode is in particular is usually in equilibrium with sodium ions. So, it can be used to measure alkali ions also, provided you make the certain changes of the measurement parameters. There is nothing much in chemistry involved in that, maybe a little bit of instrumentation. So, based on this concept, if a membrane electrode is responsive towards a alkali ion, why not have an electrode which can be responsive towards other metals also? Should be, there is nothing wrong with that. So, I can prepare a whole range of membrane electrodes made of a membrane which is responsive towards a ion, of which the membrane is responsive to the ion in solution as well as ions in the inner jacket of the glass electrode. So, only the membrane is different, again just like same principle. So, currently a number of solid state or liquid membrane electrodes are available commercially. You can name it, we have it: sodium, potassium, ammonium, cyanide, chloride, bromide, iodide, and then sulphide electrode is available, fluoride electrode is available, chloride meters are available, and you name it, we have it. There are couple of national and international manufacturers who will give you ion selective electrode, provided you have the redox measurement system. So, it is known as ORP, oxidation reduction potential. So, as I told you, it won't be exactly same as any pH meter. So that you cannot use a pH meter as ion selective electrode unless you make the range different. So, that is why most of the ion selective electrode membrane manufacturers sell the ion selective electrode as a separate unit along with the meter. So, you buy the meter, buy the electrode, and when you buy the electrode, when you want to buy an electrode, they will say, sir, do you have a meter? If you say no, then they will say, sir, you buy that meter as well as electrode from us. So, it becomes a marketing technique. So, such electrodes constitute an important part of the electrochemical research leading to the development of specific electrodes. They are called as ion selective electrodes. Nowadays, ion selective electrode, in short we call it ISE, ion selective electrodes. They are available for oxygen, chlorine, metal ions, non-metals, so many of the things. Nearly there are about 50 to 60 kinds of ion selective electrodes available from national and international manufacturers. Here in this list you can see that ISEs are available for gases, that is oxygen and chlorine, metal ions in solution, non-metal ions also in solution, etc. So, this is the typical glass electrode I had shown you earlier. It is a fairly simple technique, is not it? This we have seen earlier. There is a bulb here, and this bulb is the gas permeable membrane, and this in case of glass electrode, it is permeable to hydrogen ions. You see at the bottom a red closing the electrode. Okay. So, this whole electrode can be dipped in that, and then there is an inner solution here, this blue color, and then there is ion selective electrode here, and then we can have a meter, and then gas permeable membrane is also here. So, this could be for gas electrode. So, its most used ion selective electrode is hydrogen ion selective electrode, because that hydrogen also is an ion only. So, the most used standard is hydrogen ion selective electrode, that is pH meter. So, pH meter, as you know, it consists of a bulb immersed in the test solution. One is bulb is having 0.1 molar HCl, AgCl electrode. This I have covered number of times. Since internal HCl and AgCl are non-changeable in the potential will actually depend only upon the hydrogen ion concentration that is kept in the external solution outside the glass electrode. So, soda lime glass, that is SiO2, approximately 72%, and then sodium oxide and calcium oxide, that is known as soda lime oxide glass. So, you can, what is soda lime glass in your day to day experience is any glass that you come across which is not heat resistant. You heat it, it breaks. So, as usual, glass is expected not to have a reproducible elasticity. So, it can expand unevenly and then break. So, except some glasses like Borosil or microwave glasses what you buy outside, all other glasses if you heat them they will break. So, such glasses are known as soda lime glasses, and their composition would be 72% silica, 22% Na2O, sodium oxide, followed by about 6% of calcium oxide. All these electrodes, all these ions can be determined by ion selective electrode. If I use the same glass electrode, I can determine these elements also with a slight modification in the electronics. So, we make the membranes that work beautifully up to pH 9, but at higher pH there will be errors. So, it is not very convenient to make a glass electrode containing soda lime glass with SiO2. For SiO2 we can determine, Na2O we can determine, and calcium oxide we can determine. Nowadays membranes made of 63% SiO2, 28% lithium oxide, about 2% carbon disulfide oxide, it is not CCM, it is not carbon disulfide, yeah, it is cesium, CS2O, and then 4% barium oxide and 3% La2O, La2O3, it is not La2O. They are used with which gives an error of 0.12 pH to 12.8 pH. So, what should be the architecture of silver chloride electrode? Very simple. I can have silver chloride dipped in HCl in a glass in test solution in KCl and containing saturated calomel electrode Hg2Cl2, then mercury outside. So, when you want to make an electrode, the outermost membrane should be the outermost part of the electrode, ion selective electrode. So, the EMF of the cell may be expressed as E is equal to K some constant plus RT by NF ln AH plus, where K is the asymmetry constant which depends upon the electrode and glass membrane. The asymmetry potential varies with time, and hence a pH meter requires a frequent calibration using a buffer solution. This also we have covered earlier. Now, with H plus solution and Na plus glass, we have H plus glass and Na plus solution. So, here we make the change to convert it into sodium ion selective electrode. So, the concentration of the solution within the glass bulb is fixed, and hence an equilibrium condition is established on the inner side of the bulb, leading to a constant potential. On the outside of the bulb, the potential developed will depend upon the hydrogen ion concentration as usual, in which the bulb is immersed. So, within the layer of the dry glass, which exists between the inner and outer hydrated layers, the conductivity is due to interstitial migration of the sodium ions within the silicate lattice. That is, silicate lattice comes from the glass membrane. So, all these considerations take place when you want to make an alkaline electrode which is responsive to sodium ions or silicate ions or borate ions. So, the glass electrode can be used in presence of strong oxidants and reductants. We have there no problem with that, and then we can use it in viscous media, that is also no problem, and in presence of proteins and similar biological substances which may seriously interfere with other electrodes, but not the glass electrode. It can also be adopted for measurements with small volumes of solutions. It may give erroneous results when used with very poorly buffered solutions. So, buffered solutions are should be nearly neutral. So, obviously, the pH of buffer solution, except in few cases, would be neutral or acidic. Alkaline buffer solutions are very rare, we do not need so much, but neutral and acidic buffers we need in day to day life or in scientific life. So, here are the compositions. of the glasses. What are they? One is Na2O 22%, calcium oxide is 6%, SiO2 is 72%, and this would be used for the determination of H plus subject to alkaline error. Alkaline conditions we say do not use, that is what we have been discussing so far. Then I can use lithium glass containing lithium oxide 28%, CS2O 2%, barium oxide 4%, lanthanum oxide 3% and SiO2 63%. If I use this, I can still determine the this as a membrane. Okay. What I am trying to say here on the left side is composition. So, if I use this kind of glass, I can still determine the H plus in alkaline region, but the alkaline error will be reduced quite a lot. Now, if I want to increase use an electrode for some other elements, for example, take the third one Li2O, it has 15% Li2O, Al2O3 is 25%, SiO2 is 60%. Both these Al2O3 and SiO2 are not soluble in water. So, a glass membrane made of aluminum and silicate containing lithium oxide up to 15% should be workable for lithium ion only, because aluminum is not soluble in water, silicate is not soluble in water. Now, but I can make it make a little change here, instead of Li2O, why not go for sodium oxide. Now, look at the sodium oxide content in the top one and in the bottom one, in the third one. Here the sodium atom or sodium ion would be approximately 50% of the top one, is not it? So, I can also prepare an electrode containing Na2O and Al2O3 and SiO2, and this can work with respect to sodium and silver ion. And then Na2O, of course, I have to dope it with silver if I have to use it for silver ion. So, Na2O 20%, Al2O3 5% and SiO2 68% can be used for potassium and ammonium ions. They also would give certain amount of current that can be used for ion selective electrode. Then the construction of other ion selective electrodes is approximately similar to the glass electrode. So, how do I make a glass electrode? The glass electrode can be made into a bulb by take a glass, make the glass composition, make a tube and then blow it. So, when you blow the air, the end of the tube will be blown like a bulb. So, that is how I make the membrane, glass membrane. So, the reference electrode in all these cases would be normally AgAgCl in all ion selective electrodes. Why? Because it is a very standard system which can be easily made in any laboratory or it can be purchased also. So, the response for sodium and potassium can be increased by incorporating some Al2O3 and lithium oxide. We will have to do that. Addition or doping is a must. So, the activity of the metal ion electron response is given by the Nernst equation. Here we do not write E is equal to E naught, but we simply write a proportionality constant and then we write RT by NF log of PM. I kept it here open because I can write many things here. Usually it is P metal ion. So, for a singly charged cation I can say E is equal to K minus 0.0591 pm, that is metal ion. This P refers to negative log of concentration of the metal ion. So, if an interfering cation C plus is present in the test solution, we can establish an equilibrium something like this: metal in glass plus concentration in solution, and then we have concentration in the glass, that is equilibration, followed by metal in the solution. So, for this reaction I can simply write the stability constant K is equal to equilibrium constant, I can write, not stability. So, it is Am into Ac, Am into Ac, both are plus sign here. So, I put plus sign here, here is this thing, and single electron system. So, it is raised to 1, you can write or leave it as such. So, Am and Ac plus are the activities of the ions in the test solution, and A1 values are activities on the glass surface. Okay. So, here I am writing A1 now, A1C and A1M. So, here it works out something like this, then I can write E is equal to Km plus 2.303 RT by NF ln Am plus K M potential into CAC, where Km is the asymmetric potential of the electrode in presence of metal and concentration, and K pot MC is called selectivity coefficient of the electrode, M over C. So, KMC is given by response to C plus divided by response to M plus. This is a standard ratio given for a particular manufacturing process. So, every time you buy an ion selective electrode, the manufacturer will tell you what is this KMC for each ion. They will give you a booklet containing those things. So, KMC is a measure of the interference of the ion C plus in the determination of M plus ion, whose value depends upon the ionic concentration of the solution, and I hope you remember what is ionic concentration of the solution, and the ratio of the activity of the analyte ion to that of the interfering ion. So, now if I want to make a hydride iodide ion selective electrode, how would you go about doing it? There are different ways of preparing the membrane. You see, the whole problem of determining making an ion selective membrane is to make the membrane responsive. So, I can do it by incorporating while melting and make the membrane and blowing, glass blowing, I had shown you earlier, explained earlier, or I can simply distribute these ions into a silicon rubber monomer and carry out the polymerization. So, the ions which are around on the membrane will be embedded in the polymer. So, the finely powdered silver iodide can be dispersed into a silicon rubber monomer, and polymerization should give me a silver iodide membrane. So, silver iodide membrane should be useful for silver as well as iodide. So, I use a small, make a membrane and then cut a small piece like this, a small 1 centimeter this thing, fit it into the ion selective electrode bottom layer, and then outer layer is my test cell, inner layer is standard solution or saturated solution with silver chloride electrode as the reference electrode. So, the inner tube is filled with 0.1 molar Ki solution in this case. If it is calomel electrode, mercury. So, insert a silver wire into silver iodide, that is our silver iodide electrode. So, when a test solution is to be measured, we have a silver iodide in the solid form, that is the membrane, that is the solid, and in contact with hydrogen iodide, that is in contact with the membrane, and then the whole thing is having a salt bridge separation, double line like this represents salt bridge separation, and then KCl, and then Hg2Cl2 by Hg. So, that means we are using a mercury saturated calomel electrode as a reference electrode, because AgCl I cannot use, because there will be some problems with silver. So, best when you want to use silver chloride, do not use AgCl electrode, but you can go for mercury chloride mercury electrode. So, now I want to describe a lanthanum fluoride electrode. Here a single electrode in which lanthanum fluoride is sealed into the bottom of a plastic container containing KCl and Kf with silver chloride electrode at its lower end. So, silver chloride would be the reference electrode. So, fluoride ions can move through the crystal from one lattice defect to another lattice defect in equilibrium, and equilibrium will be established between the crystal phase inside the electrode and the internal solution. So, when the electrode is placed in a solution of fluoride ions, equilibrium is established at the external surface of the crystal, and the fluoride ion activities at internal and external surface are different, leading to the potential difference which is proportional to the fluoride ion activity of the solution. Now, I want to tell you there are many other electrodes. I am describing fluoride electrode for the first time here in this program, because fluoride is a very big contaminant and toxic element in the bowels of the earth. You know, we dig water and from the borewell it comes, and everywhere there is fluoride nowadays, and fluoride is not good for health. WHO prescribes 1 to 1.5 ppm of fluoride in drinking water. So, fluoride ion electrode is a very important activity or a very important gadget one can carry around if you want to determine fluoride. So, we will continue our discussion in the next class about ion selective electrodes, and then we will move on to sensors. So, thank you very much.